Hello everyone, welcome to this week's video. So as promised, we're going to be start looking at our CADs. So I feel like the most important thing is the probe itself. So let's look at the probe in its deployed state. And so we have CAD here. Yes, this is how I'm going to orient the probe during this video. Don't mind these. Don't worry about this. So again, this is a pretty small probe. If we look down topside, this is, has a diameter of, I believe, 850 millimeters. So we're looking at about 1.3 meters in total diameter, including the extended panels. So the actual probe body itself, can I zoom in? Hello? One of the big issues with this model is, of course, I've got our beautiful crush zone. And of course, one problem with our crush zone is there's so many hexagons that it has to draw a lot, is what I'm saying. So we've got this hexagon here, which is our primary bus. So this is where the electronics is, the heater, and of course the battery, the MPPT, maximum power point tracking power converter system that we'll use. And so it also holds the radio transmitters and receivers. We have dual transceivers on the probe, as mentioned before, and our antennas are actually in these top sections, I guess. This block here is also where there's a helical antenna, but it's actually primarily as just a mechanical protectorant of the rest of the probe during launch of the probes and entry into Mars. So yeah, these are basically where our antennas are stored. This is our main bus that is like insulated with our cork and then MLI insulation. And then we've got just a thin aluminum panel here. It is just 5 millimeters, and it is mainly to spread out the force impact from the crush zone, which is all here. I don't remember the exact specs, admittedly. That's in a past video, but as you can see here, it's pretty dang thin. So I guess I can't see. Will let me. No, it will not play. Nice. Cool. Okay. But that's not the point. So that's our crush zone. It will not be able to absorb all of the energy of the impact, but the probe itself is designed for 300G with full operation status. And that's with a safety factor of 1.2. And that's what our panels are expected to hit maximum before they are unable to deploy. And then they're folded up where this last panel here on each side will be facing out and up at a 45 degree angle. What's colored wrong in this model is okay, I don't need to measure. This is actually an additional panel right here. Of course, it is blocked by the actual probe bus, but it is there, always deployed, and its one segment is a little bit larger than any one of the 4 of the 3 deployable sections. Okay. One notable thing about the probes, so I'm just getting my models here. So here's exactly the same. Technically, this model, I just made it so the crush zone is a sphere, or a cylinder, sorry. And then this is our aeroshell. So this is our aeroshell where the probe is, and the probe is again stored upside down. We've got that little protectorant nubbin, essentially. And so that is stowed downwards. But of course, we're downwards and we need it to be right side up. So how do we do that? The answer is due to the lack of forces during the parachute section of the probe. We essentially just have the track of the parachute. So this nub is also where the parachute is attached to the probe. And it simply just goes in this little channel here. Pretty simple. And it reorients the probe like that. Okay, so let's talk about some of these sensors that are on the probe. So first we're going to talk about this one. So this is our anemometer, and it also has an antenna in here for static discharge. So we'll be able to detect static buildup and lightning detection. And you might notice that let's say we take a side angle here, we are blocked by the probe. That's okay. We have another anemometer right here. This has a split cut in it to help. So this entire surface area, because they're solid state anemometers, they just measure based on the difference in temperature. This kind of works like a pitot tube where you have a more stagnation zone. All of the exposed probes have a temperature sensor. And alongside these panels on the underside, we'll have temperature sensors, and that's just to create a better band of knowing, so we can compare the wind to make it more precise. And they can also be used as rough anemometers. And then our main cluster, I'm not using a mouse, so my apologies for the reorientation of the probe, just using my cursor. So we've got a camera here, another camera here. And so what's important about these are pretty simple. This is our main optical stills camera, that is the side angle. And what's notable about that, is basically that this is our side angle. So we have a downwards angle and a side, and so that's for our visual. And then this is our thermal camera, because we also have a thermal camera. It's an incredibly low resolution, and that's on purpose. And then here we've just got more temperature and barometric pressure sensors. Pretty simple. Also, you might have seen that we have a little protrusion here. This is our downward facing radar. Note that even though it goes through the honeycomb, it's not actually affected by the honeycomb at all. So it doesn't actually matter. And that's to get better precision on our altitude. Okay. So our next sensor is here, and this is again kind of just more of the same general meteorology sensors. And then here is our downward facing camera, and it has a telescope, a longer focal length, which is why the lens is so bulbous, I guess would be the term. And so that's just for a straight down, because the probes will be transmitting on their way down during the EDL phase of this mission. And basically, let's say that something occurs poorly. Well, we still want a very good high-res photo of the descent, or photos of the descent. So that's what they're for. So that's kind of the basics of the probe. There's a little bit more to it, but in terms of external features, that's really all that matters. So with that, thank you very much for watching. I hope you have a wonderful day. Bye-bye.